Hello friends, this is Dr. Saikrishna from IIT Tirupati. So I would be dealing with this module 12 of this course, which talks about practical aspects of control design. Okay, so what does it mean by practical aspects of control design? So we might have already gone through the control design in terms of so-called PID controllers. All right. So what we'll do in this module with respect to several submodules is that we will move towards the, uh, the PID controllers, starting from discontinuous control modes and navigating towards continuous control modes. Okay, so PID controllers are actually continuous control modes. However, we start with the discontinuous control modes and then move towards the continuous control modes, which are the PID controller. Okay, now once we talk about PID controllers, the evolution from the discontinuous to continuous control modes, the next step we are going to do is we talk about the Ziegler Nichols method for control tuning in detail, and then we'll talk about the reset windup and anti-reset windup and solutions for reset windup in a PID controller. All right, and then we'll end up with the numerical examples. All right. So first, what we do is we start with the first submodule of this lecture series. This is one of the submodules, right? So what we do in this submodule is we talk about introduction to controllers and control modes, and then later we go into detail about each of these topics. Okay. So let's start with understanding what is a controller. As all of us know, a controller is used to control a system. Okay, essentially controlling a system actually means that we control a variable under consideration. Okay, so let's try to understand this the concept of controller with a simple example wherein you have a tank. You can see the tank here, which is currently at a height h, and we want the height of the tank to be capital H. Okay, so we essentially have the height of the tank to be small h, and we want the height of the tank to be capital H. All right. So now what we can see here is that we have something in control here. Okay. So what is that variable which is under control here? We do not know right now. Okay. So we have a certain inflow here, we have a certain outflow here. Okay. Water is getting into the tank and water is going out of the tank. All right. And if the dimensions of the pipe, of the inflow pipe and the outflow pipe are the same, and if the flow rate is the same, the tank would remain at the same level at all times. All right. Now the objective is to get the height of the tank to capital H from small h, and we are clear here that it is very clear that small h is greater than capital H. All right. So we need to reduce the level of the tank. Okay. So assume that you are able to operate a control valve at the outflow. Okay, there is a control valve at the outflow which can be used to manipulate the outflow. Okay, let's say the inflow is uncontrollable, and then outflow is controllable by means of a control valve. All right. So in such a case, what we can do is, depending on the inflow rate, there could be a change in level h, and therefore the idea is to manipulate the outflow so that the level settles down somewhere at capital H. Okay. So this is a very simple control system where what I have done is I have just kept a control valve at the outlet and tried to manipulate the outlet flow so that the level is maintained around H. Okay. Why I am saying around H is because there could be various disturbances and there may not be a possibility that H would be constant. Okay, it may vary over time. Fine. So let's understand this by means of a manual control system, right? manual control system. It means that, as I told you just now, that we have a valve in the outlet which can be controlled. All right. Let's say we do it manually. Okay. If I have to do this manually, then the only thing I can do is to see here. This instrument is called side glass. All right. So this side glass, you can have a look at it and then see the level of the tank, and this is the actual level which is shown as H, and this is the desired level which is H, okay, capital H, alright, and you want the desired level to be at H, capital H. Now you can open this valve either clockwise or anti-clockwise depending on the situation here. You want to open the valve or close the valve here, and then you would like to manipulate the outflow here. Alright. So if you manipulate the outflow here, then you could possibly reach this height of capital H. Okay. So here what we have done is we are operating the valve manually. Alright. We are operating the valve manually. So now when we operate the valve manually, we are first looking at the side glass which serves as a kind of measurement here. Okay. Which serves as a certain measurement here. Alright, so in case we want to make this control loop to be automatic, right, that means that we should be able to see the deviation between the actual height H, okay, and the desired height H, okay, and based on this deviation we calculate an error E, and then based on that we can rotate this outlet valve appropriately in a certain direction to keep the level close to capital H. Okay. So in case we want to do that, then this comparison which we have to make between small h and capital H has to be done in a certain hardware. Okay. In a certain hardware. So that hardware is called the controller. Okay. So what would the controller do is it would see the reference, which is the capital H here, and the measured signal, which is a small h here, and it would calculate the difference between them, and it would calculate the error, of course, and based on the error it would run a certain algorithm which would drive something called an actuator. Alright, an actuator, and this actuator would finally drive a control valve. Alright, so this is a control loop here. Okay. Now, the most important thing to understand here is that how would the controller understand what is the height, okay? Because when we were doing this manually, we were able to see it in a side glass. It was very clear that height is lower or higher, we are able to judge by our eyes, alright? However, if you have a controller, how does it know it? Okay, so there should be a means in which, by which you should take this sensor reading and convert this into some kind of signal, okay, some kind of electrical signal. All right, okay, so you should convert this into some kind of electrical signal. Why do we need to convert this into electrical signal? Is because once we convert this into electrical signal, we can easily compare the reference could be an electrical signal, and the measured signal could also be electrical signal. Both of these we compare and we can get an error, and based on the error we can run an algorithm which will be used to drive the control valve via an actuator. Okay, so this is the way the control loop would work. Right, so this is called a closed loop control system. Okay, this is called a closed loop control system. All right, and we also called the controller to be an automatic controller here. All right. Now this is what I was just telling you just before in this previous slide, that we have a certain reference R. Okay. In our case, the reference R is capital H, and the measured value is small h. And then once we take the difference between them, we get the error, and this runs a certain algorithm which can be used to generate a controller output. Okay, so this can be called as a controller output. Generally, this is represented by either small p, sometimes by u, and so on. So different textbooks have different notations for this. Okay, don't need to worry about the notations now. All right. So conceptually it is very clear here that you just have a reference, you have a measured variable or the actual value of the system, actual value of the variable. Okay, so this is the actual value of the variable. Once you take this difference, you get the error signal, and then a controller runs the control algorithm based on the error signal, and you get the output, and this output goes to the actuator. Okay, and then it drives the valve. Okay, so this is the control loop. Okay, so now, so how does it happen actually in industries is as follows. Okay, so you have various sensors on the plant side. Okay, and you have a control room here. Okay, so there are two places here between which the exchange of signal takes place: the control room and the plant. Okay, there can be various sensors in the plant side, and there could be a centralized place called the control room where via certain hardware you receive all the control signals, okay, or the measured signals. All right. Now what do we do here is that, let's say for example we take a pressure sensor here. Okay, so what do we actually try to do is we first convert the pressure signal into current signal via a hardware called transmitter. Okay, this is called the transmitter. So transmitter is a hardware which would convert a pressure signal to a current signal. Okay, so this conversion is done in the most standard form, which is called 4 to 20 milliamps range. Okay, so 4 to 20 milliamps is one of the most is the standard of change of a physical variable to current. Okay, so you have a physical variable or measurement. All right, and this variable is converted into current in the range of 4 to 20 milliamps. Okay, so here pressure could be, let's say for example, 0 to 50 psi. Okay, psi means pounds per square inch, and then you are converting this proportionally towards 4 to 20 milliamps. Okay, so this is the way conversion takes place. You could also have a temperature sensor wherein you convert 0 to 100 degrees probably to 4 to 20 milliamps. Okay, so 4 to 20 milliamps is the most standard form of current which we encounter in industries. All right. Okay, fine. So the same thing, if we need to take a control action, right, from the control room towards the plant side, for example, to operate a valve. Okay, so what do? There are two ways of doing it. Okay, since the hardware exists for these two ways, I'll just tell you what are the possible options. The first option is you consider taking a voltage, okay, which comes from the controller, all right. This control output is the voltage, okay, and this voltage can be directly converted into pressure. Okay, this is the pressure. All right, so let me just put this line is a pressure line. Okay, and this pressure line operates over 3 to 15 psi, even though 3 to 15 psi is a very low pressure, and there should be some amplification of this pressure taking place in between. Okay, there should be some kind of amplification which is not really shown in textbooks. All right, and this is also called volume booster. Okay, this is also called the volume booster. Okay, so now the controller output, as we have seen before, is given in terms of a voltage. Okay, and the standard voltage range is 1 to 5 volts. All right, so 1 volt means the control output is considered as 0. 0 means you can consider 0%. I'll tell you the notations of percent little later in the problems. All right, and 5 volts means 100%. All right, so this is the way in which you have the controlled output scaled from 0 to 100% in terms of voltage. Okay, so 1 to 5 volts is actually converted to pressure directly. Okay, that is one possibility. Okay, if it is not possible to convert 1 to 5 volts directly to pressure by a hardware like this V to P converter, then in such a case what we do is we convert voltage to current. All right, and then current to pressure. Okay, and why do I use current now? Because generally this is very traditional. This 3 to 15 psi transmission is very traditional one. It was used several decades ago. Okay, so nowadays we don't use directly a pressure line for control. So what we try to do is we transmit this control signal, which is in terms of voltage. We transmit it, we convert it into current first, and then at this end probably we could use a I to P converter. That means you could use this to be I to P. That means here you would not use all this. Let me rub this off. So that means what will I do here is I would take voltage, then I would take this conversion of voltage to current. Okay, so you are transmitting the current here, and then this current you convert this into pressure. Okay, and this pressure of course will be able to drive the actuator, and actuator will be able to control the final control element, which is the valve. Alright, so this is the way wherein the closed loop control works in an industry. Okay, so you are sensing something. Okay, you are able to sense something from the plant side, and you are able to control from the control room side. Okay, so this is the way the whole control loop works. Okay, so the same control loop what we have seen here, right, in this level control system can be drawn for a control system like this, a pressure control loop. Okay, so only difference would be that the controller would be in the control room. Okay, controller would be in the control room, and so let me just write this as control room. It's a column here, so let me write this as control room. Alright, and the sensing part, this could be the plant. Okay, this could be the plant side, this could be the plant side, this could be the control room side. Okay, so the controller and the plant means the water tank with all the accessories would be separated by a larger distance possibly, and the transmission could be in terms of current. Okay, larger the distance, you would prefer more, you would be favorable more towards current transmission. Okay, if the distance is shorter, then you would go for voltage transmission. All right, so that's the thing about the closed loop control here. Okay, so what do we see in this module? As I told you that this module will be covering several topics. So I would just give an overview of what are the topics which we are going to cover further in this lecture series. Is first we talk about the control modes. Okay, so is it a continuous control action or discontinuous control action? Okay, that actually means that for a continuous control action, for every change in error you can see a change in control output. For a discontinuous control action, you may not be able to see that. You will see that for a range of errors there will be a control action. Okay, for a range of errors. But for a continuous control action, you would see that for a given error there would be a corresponding control output. Okay. Now the second classification we have is the direct control action and reverse control action. Okay. Direct control action means that as the error increases, okay, as the error increases, the controller output also increases. Okay, so that is direct action. Okay, if the error is increasing, the controller output will also increase. Okay, reverse action means that if the error is increasing, the controller output is decreasing. Okay, this we can only relate with respect to certain examples which we will see as we move on in this module. Alright. Now, as I told you that there are continuous controllers and discontinuous controllers. Okay, and they are divided into a certain set of controllers here. You can see here clearly that the first three, okay, come under the continuous control. Sorry, the discontinuous control modes. All right, discontinuous control modes. So from here you will call these as continuous control modes. Okay. So this is called continuous control modes. So what we do in this series of lectures is that we would deal with each one of these control modes, see their working, what are the parameters which are needed to tune so that the performance of the controller is satisfactory, is what we will see in this module. Okay. Now, before getting to the next module, we will solve some numerical examples to understand the closed loop part which we tried to discuss in the example, level control example. Alright. So let's start with an example so that you get into understanding what is this 4 to 20 milliamps and so on. Okay. So let's take an example here. So what is this example says here is that suppose the temperature range is 20 degrees to 120 degrees is linearly converted to a standard range of 4 to 20 milliamps. Okay. What current would result from 66 degrees? What temperature does 6.5 milliamp represent? Okay. So what is the fundamental question here, right? So we are dealing with a temperature range of 20 degrees to 120 degrees Celsius. All right. And this is getting converted to a current signal of 4 to 20 milliamps. All right. Now this is a kind of linear conversion. All right. So this is a kind of linear conversion, and we need to relate the temperature, okay, to the current, okay, to the current. So first, if we understand this, then we can actually develop the corresponding hardware to do that. For example, if we have to do this conversion mathematically, you can just write y is equal to mx plus c, right? So y could be the current, all right. So y is the current, and x could be the temperature, okay. X could be the temperature. I would call x to be the temperature, all right. So what would I do now is, using this equation y is equal to mx plus c, try to see how temperature is mapped to current, okay. So let's try to see that. So first, if you see output, let me call it as current. So 4 milliamps current is equivalent to, I'm not putting units here, okay, for convenience. So it would be easy to understand as well. So m into temperature, right? This is 20. So this is 20 plus C, okay. So similarly, you have 20 milliamps is equal to m into 120 plus C, okay. So these are two relations which we can achieve from the given information, okay. So once I do this, it is very clear that m and c can be solved. So let me just give you the values of m and c which can be obtained here. M is found to be 0.16 and C is found to be 0.8, okay. So once we find these two values of M and C, we can actually relate temperature and current for any given value of either temperature or current in this range of 20 degrees to 120 degrees or 4 to 20 milliamps, okay. So the first question is, what current will result from 66 degrees, okay. So you have the relation here. So what is y? Y is the current. M is already found here, 0.16. Let me just change this y to current I for convenience into T. This is plus C, okay. C is, let me just replace the value of C also here. C is 0.8 here, okay. Now we substitute T is equal to 66 degrees Celsius, then I can be found here, okay. So I can be found to be 11.36 milliamps, okay. This. So that means that if you are looking at a temperature in this range, 20 degrees to 120 degrees, and you want to map it to 4 to 20 milliamps, then you can find that current is 11.36 milliamps, alright. So second thing is here, what temperature does 6.5 milliamps represent? Okay, 6.5 milliamps is equivalent to what temperature? Okay, so I'd use the same equation. 6.5 is equal to 0.16 into T plus 0.8. Okay, so this is very simple to understand. Okay, so you can find T as 35.62 degrees Celsius. Okay, this is very simple to understand. This is the way to solve this problem. Okay, so what are we essentially trying to do? We are trying to map the temperature with respect to the current. Okay, so the temperature range is 20 to 120 degrees, and you have the current range to be 4 to 20 milliamps. Okay, and then we are trying to figure out, if we pick up a value of temperature in the range 20 degrees to 120 degrees, what could be the corresponding current? Similarly, if the current is given in that range of 4 to 20 milliamps, what could be the temperature? Okay, so this is the way to solve this problem. Okay, fine. So let's go back to the next question here. So what does it say here? So you have here temperature of 300 to 440 Kelvin. Okay, and you have a set point of 384 here. Okay, now what is the question here? Find the percentage of span error when the temperature is 379. Okay, what does it actually mean? So this question actually means that you have a kind of temperature control system wherein the actual temperature is 379 Kelvin. Okay, and the set point, okay, set point is given as 384 Kelvin. Okay, and then you want to find out the percentage of span error. What is the error here? The error is equal to reference, let me just write it here properly, reference minus the actual value. So what is the reference here? 384 minus 379. Okay, so this is the value which we need to find. Okay, this is the error. Okay, so error is equal to, this is Kelvin, right? So this is coming out to be 5 Kelvin. Okay, absolute error is coming to be 5 Kelvin. Okay, what does it mean by percentage of span? Okay, so first we need to understand what is span. Okay, span is the highest value of the range minus the lowest value of the range. Okay, let me call this as Cmax minus Cmin. Okay, Cmax means, or I can call it as Tmax minus Tmin. Anyways, Tmax minus Tmin. So this could be 440 minus 300. This is Kelvin. Okay, the span is the difference between the highest value to the lowest value in the given range. Okay, now what does it mean by percentage span error? So for percentage span error, what we need to do is we need to calculate the error. Let me just write this as, this is equivalent to, alright, so this is reference minus B minus actual value, or you just leave it as it is. You can just write 384 minus 379 is the error divided by the Tmax minus the Tmin. Okay, Tmax minus the Tmin. Okay, in 200. Alright, so this would give you the percentage of span error. Okay, that means if the error is 5 Kelvin, it falls into 3.57% of the span. What is span here? Span is equivalent to 440 minus 300. Okay, so this is around 140 Kelvin. Alright, this is a way to define the span. Alright, fine. Let's try one more problem here before we close this module. So you have a system wherein you have a controller which outputs a 4 to 20 milliamps to control a motor from speed 140 to 600 rpm. Okay, with linear dependence. Okay, So let me just quickly draw a control loop here. Just you have this reference, this is the actual value, okay. You have the controller here, I'll just put it as C, and I'll just put plant as P or the process as P, and there is some kind of transmission here in the back, okay. And this transmission is 4 to 20 milliamps, okay. I'm not showing any hardware to show the processing of 4 to 20 milliamps and so on, okay. So essentially what you are trying to do is, in the output, you are trying to control the speed from 140 to 600 RPM, okay. You are trying to control the speed from 140 to 600 RPM, okay. And the reference speed would be depending on what speed is desired, okay. This is the way to calculate. So you have to give some reference. Based on that, you are going to see the changes in the output due to the controller. You are going to feed back the actual measurement, which is in terms of 4 to 20 milliamps, okay. So this is the basic control loop here, okay. So what is the question here? So if 4 to 20 milliamps is corresponding to 140 to 600 RPM, calculate the current corresponding to 310 RPM. This is a very simple example as we did before, but I just wanted to show you the control loop, so I picked this example for you, okay. So you just use the linear dependence, y is equal to mx plus c here, as usual. What you call here the output as the speed and this x as the current, okay. So just by applying your dependence between the current and speed, you can write 140, which is the speed, is equal to 4 into m plus c, okay. Similarly, you have 600 RPM is equal to 20 into m plus c. So 4 and 20 are the currents here, okay. These are the speeds, okay. And from here you can actually find m to be 28.75 and c to be 25, okay. And therefore you can easily calculate the part A for 310 RPM. What will be the corresponding current, okay. So you write 310 is equal to 28.75 into I plus 25. So you can actually find I here. You can actually find I here, which will be equal to around 9.91 milliamps, okay. So next question is the value of A expressed as a percentage of control output. What does that mean? So you want to assess what is the value of current, which is 9.91 in terms of percentage of control output, okay. So what does it actually mean? So as we did before, so what we need to do is we need to subtract this value, okay, from the minimum value of the range, that means 4 milliamps, right, divided by 20 milliamps, this is a span, okay, and this is multiplied by 100, okay. So this will give you the percentage of control output, okay. Where does this 9.91 lie in the range of 4 to 20 milliamps, okay. So this would be approximately 36.9%, okay, 36.9%, okay. So these are a couple of examples which will help you to figure out how the measurement especially is mapped to a certain variable. So the measurement in terms of current, how are you mapping it to a certain variable here? Here the variable is the speed, okay. So this is the control loop which you can understand very clearly, that you have a reference, you have the actual value, you have the controller, you have the plant, okay, and this is the way in which you run the closed loop control, okay. So these are some references which I've used for making this presentation. First is Johnson, Curtis V. Johnson, Process Control Instrumentation Technology, Seaborg, Process Dynamics and Control, and Franklin, you have feedback control of dynamic systems, okay. So these are the textbooks you can use for getting into detail on these basic type of aspects on control. and then also you can find several numerical problems which you can solve. Okay, thank you.